so just to recap so far, right, we've got electric fields, the things that are around anything that has a charge. We've got magnetic fields, which is produced whenever a charge starts to move. We've got the motor effect, which is whenever we have a current in a magnetic field. And now we're moving on to induction. Now, I'm not going to lie. I reckon induction, or at least parts of induction, are some of the hardest in the syllabus, at least the hardest to wrap your head around. So if you don't understand all of this just by watching this video, don't worry. I was very much there. I don't really think I understood a lot of induction even by the end of year 12. It took me quite a while to wrap my head around stuff like Lenz's law. So it's a little bit of a whack topic. So yeah, don't worry too much if you feel a little bit overwhelmed just by this section. It is a perfectly normal feeling. You are normal. Anyway, what is electromagnetic induction? There's this guy, James Faraday. I actually don't know if his first name was James. James Maxwell. Sorry, I saw the word Maxwell, and I know Maxwell's first name was James. Not sure what Faraday's first name is. Either way, Faraday discovered that when he passed a current through a coil, a small current appeared in adjacent coil. It turns out he could get the same effect by moving a magnet. Just to recap that, basically he set up this little circuit down here, and he noticed that when he turned the current on in his circuit, and just to be very specific, this is sort of two separate circuits. Maybe to draw it slightly more abstractly, you've got your battery pack over here, you've got a little switch, and then you've got just your current here, and then this is a little ammeter, a little thing to like measure the current. And he noticed that when you close the switch, very briefly, you measured a little tiny current over here. It didn't stay constant. It was just sort of like you close the switch on one side, and then the current just like briefly flicks. You get a little tiny bit of current on the other side. And eventually, this was later measured by our favorite friend, James Maxwell, as Faraday's law. Maxwell's not going to be our favorite friend until Module 7, though. But once you get to Module 7, we love him. We stan Maxwell. Okay, and we call it Faraday's law. They're both very cool. Now, electromagnetic induction is defined as when a conductor exposed to a change in flux induces an EMF. Yuck. All right, there's a couple of things that we need to dig into. What is a flux and how do I use it? And what is an EMF and what the hell happens there? So, first of all, answering the first of these questions, what is a flux? Flux is defined as how many things are going through an area. So you can sort of imagine the flux of, say, a room of people is just how many people are in the room. So if we have, a big auditorium, it's probably got a higher, flux of people than, say, a car. There's only going to be 1 or 2 or 3 or 4 people in a car, whereas a big auditorium probably has a lot more people. Whereas flux density is basically how packed these things are. That determines what we call the field strength B. Now, another way of thinking about flux is you have a whole bunch of things, but then oftentimes you kind of need to force them through a very, very small area. Like you can imagine if you've got your big auditorium of people and there's a fire evacuation alarm, you've only got like that little tiny doorway of space for stuff to go through. And so as a result, you're trying to squeeze a whole lot of people into a very, very small area. And that is going to cause some interesting squeezing problems. Now, for the purposes here, we don't really care too much about people and the flux of people. What we're interested in is what's called magnetic flux, which is basically just a measurement of how many magnetic field lines are in a particular area. Basically, how much strength of magnetic field is in a particular space. So down here, I've drawn 2 little areas. You can sort of see how in both of these situations, the amount of magnetic flux in both of them is exactly the same, right? They're both capturing 4 magnetic field lines. However, there is a key distinction between the two, which is that you can see in one of them, all of the field lines are nice and packed tightly in together, whereas in one of the other field lines, they're really quite spread apart. And that's because even though they both have the same flux, they do not have the same flux density, because flux density is how tightly packed those two things things are going to be. So going back to the auditorium example, even though you might have like, I don't know, 100, if you imagine like an auditorium versus a car, you can fit you can fit maybe 10 people into both of those cases, right? But in a massive auditorium, 10 people is going to feel much less dense than trying to fit 10 people into a single car, right? And only one of them is going to get you arrested by the New South Wales police. I mean, it depends. Yeah, anyway, I'm not going to get into that. So yeah, the flux is how much stuff is actually in an area, whereas flux density is how packed those things are into that particular area. That's what flux is. That's what magnetic flux is. But what we're also interested in is, well, what's an EMF? Now, the definition of EMF is electromotive force, but for our purposes, it's basically a voltage. Like it's measured in volts for our purposes. So you can basically read this as a voltage. And in fact, because in like 97%, I know I keep on using these really specific high numbers, but in like 97% of cases, when you read EMF, you can basically just read it as current. It basically means that there's some kind of current induced. So electromagnetic induction, to sort of put it in kind of layman's terms now, electromagnetic induction is the effect that occurs when you have some kind of wire exposed to a change in the magnetic field lines around it that induces a current flowing through it. So flicking back a couple of slides, we can go back to this situation and we can see what was happening was when you turn the current on in this field, suddenly we have some kind of current flowing through the wire. And because we know from our right-hand grip rule, that's going to induce a magnetic field. When we turn the current on, we go suddenly from having no current to having some current, which means we go from having no magnetic field to having some magnetic field. That is a change in magnetic flux because we go from having no magnetic field lines to having some magnetic field lines. And based off electromagnetic induction, or Faraday's law, that says that should induce an EMF, which in this case, because it's a nice closed loop, is going to like manifest itself in the form of an actual current, which is a lot of fun. So yeah, so for most of our purposes, it's a voltage, which most of the time will just be a current. So to recap, previous slides, our magnetic flux is the amount of magnetic field, which is basically just us counting the field lines, whereas our magnetic flux density is how much magnetic field is in there per unit area, which is basically just how densely packed the magnetic field lines are. And as it turns out, our magnetic flux density is actually the magnetic field that we've been talking about so far, right? That magnetic field is measured here as like our B, which means we can actually use this to kind of come up with a formula to calculate magnetic flux, right? Because if our magnetic field is the magnetic flux per unit area, i.e. B is equal to how much flux we have, and sorry, that was a horrible flux sign, how much flux we have per unit area, where this is like our area down the bottom, we can rearrange this formula to get that our phi, our magnetic field flux, is equal to magnetic field times by our area. And that is what we find out is exactly the formula down below. Our magnetic field is equal to phi divided by A, and our flux is equal to the magnetic field times by our A. Now, I'm not sure if I said it explicitly, but this Greek character is called phi. It's the Greek letter phi. We're going to use it a couple of times in the next few modules for various things, but it's just a circle with a line through the middle. It's nothing too fancy, and it represents our magnetic flux. Now, our magnetic flux density is, sorry, I should just call it our magnetic field is measured in Teslas, as always. Our area is measured in meters squared, and then in my opinion, I reckon flux kind of takes the cake for the funniest sounding units that we're going to deal with in physics. But it's measured in Webers, right? So our little shorthand for it is WB. The longhand is Weber, or maybe Weber. I promise you, it's not one of those like little tiny cook stoves or whatever, barbecues, but that is the units that we're going to be dealing with. Now, the formula that you are given on your formula sheet is this full one. Once again, just ignore the theta, or try and ignore the theta. Once again, we sort of get a maximum flux when a magnetic field is passing through a particular area perpendicularly. And so as a result, I like to, if you're going to include the theta, I kind of prefer to think of it as be a sine theta, where theta is the angle between kind of the plane of your surface and your magnetic field. Because in the way that it's written at the moment, what this theta actually represents is if you have some surface, if you imagine you have a normal to the surface, if you can kind of pretend you've got some angle sticking up perpendicularly to your surface, that's what a normal means. It basically means if you've got like a flat area, if you've got something that's like sticking out perpendicularly to your surface, that's what we call the normal. The angle here, this angle theta, is the angle between your magnetic field lines and your normal. Not with your surface, with your normal. It's basically the angle between these two, which, like, if you think about it for a second, like, it does kind of make sense, because it means that you then have zero when the normal is parallel to the magnetic field lines, which is the same as having the magnetic field lines going perpendicularly to the surface. But just like in that case, do it perpendicularly to the surface and use sine for the first case. Anyway, all that being said, you will get a maximum. You have maximum flux passing through when you have a like perpendicularly, basically. Um, so yeah. The other way it's kind of written on your formula sheet is you have perpendicular magnetic field. Sorry, you get a maximum flux when your magnetic field is perpendicular to your area. So let's actually jump into this question. I've done enough ranting at the formula. Let's try and actually do some stuff. As always, you can do the practice if you want to down below. I really encourage you to because it will mean that you'll like digest it a little bit more. Okay. Um, so we're trying to calculate what our magnetic flux is. Basically, we're trying to figure out what is our phi equal to. Um, we know that the magnetic field has a magnetic field strength of 3 Teslas. So let's jot that down. Our magnetic field strength is, I just wrote T, it's 3 Teslas. Um, and it's in a circular coil with a radius of 2 meters. Basically, we've got some kind of circle with a radius of 2 meters, and we need to calculate the area of this, right? Because we want to know how big is the space of this coil. So in order to do that, we're going to use the formula. Our area of a circle is pi r squared. So chucking in r, we get our area of the circle is pi times 2 squared, which is equal to 4 pi. You can evaluate that on your calculator, but just for the sake of like, look, I'm a math student, I like to keep things in exact form. We can write that as like 4 pi. And then finally, we can chuck this into the formula. We get our phi is equal to 3 times 4 pi, which is equal to 12 pi. Which, you know what, let's chuck it into the calculator to get a feel for how big that is. That is 37.699 Webers, or Webers, or however it's pronounced. But yeah, that's how we calculate our magnetic flux. However, that was only half of the definition, right? The other thing that we had to deal with was EMF, and just like flux, we actually have a formula for EMF as well. Now, Faraday's law states that relative motion between a conductor and a magnetic field induces an EMF. This is just a fancier way of defining the electromagnetic induction that we dealt with before. It's a slightly more rigorous definition. It basically just says that you can kind of interpret it in the same way, right? So beforehand, we said that any kind of change in flux, any kind of change in magnetic flux is going to induce an EMF. This is basically just saying that instead of saying a change in flux, it's saying relative motion between a conductor and a magnetic field, which they may not seem it, but they mean the same thing, right? Because a change in flux is basically you've just got some kind of change in magnetic field. This is basically just saying like if you change something between a conductor and a magnetic field, it's going to cause a change in flux, and so as a result, it's going to cause an EMF. Now, the size of that induced voltage is directly proportional to the rate of the size of the magnetic flux. Basically, you have this formula here. Now, if you've never seen this little like half or 3/4 infinity sign, it basically just means proportional. If you're not super comfortable with the idea of proportional, it basically just means the only thing that's left is some kind of constant or some kind of like proportionality thing. So we could kind of write the full formula as being epsilon is equal to minus n delta phi on delta t. Where n is some number, but it actually turns out that it actually does have a particular use in this case here. Um, Now, a couple of quick notes. First of all, if you do advanced maths or pretty much any level of maths aside from standard, this delta phi on delta t, you can actually interpret this like just intuitively. You can remember this is actually a derivative. It's basically like the real formula has a derivative in it. It's just that because we are a no calculus course here in physics, we want to make every excuse to not touch on calculus, so we make the delta phi on delta t. But for example, if you have a question that's asking you to like draw a graph of to like sketch out or like identify which graph has the flux, you can just remember it's the derivative, so we're dealing with gradients instead. If you don't do advanced maths, that's fine. You don't have to worry about it because like it is designed so you don't need to know that it's a derivative. I just find that if you do know it's a derivative and you like derivatives, I prefer to think of it that way. The other thing to make note of is the negative. Um, It basically is because of the law of conservation of energy. It means that stuff doesn't die, and we'll talk about it a bit more in just a second. But here is a lovely little moving picture that some pronounce GIF and some pronounce GIF. GIF is the correct pronunciation, by the way. That sort of shows us what's going on. So you move a magnet inside some kind of coil, and it will induce a voltage as a result. Yeah, we'll dig into it a little bit further in just a second. Now, sorry, I thought I did have it on my slides, but the full formula is, and the formula that you're given on your formula sheet is epsilon is equal to negative n delta phi on delta t, where epsilon is our EMF. Epsilon is our EMF, which is measured in volts. N is the number of coils in our is the number of coils in like whatever thing we're inducing a current in. So for example, here you can see that there are a whole bunch of coils. You would just count them up, and however many there are, that's your value of N. Delta phi is how much flux is changing. So I'll show you how to do that in the next example, but usually it's going from like some very small amount of flux to some quite high amount of flux. And then our delta t is whatever change in time is occurring. Basically, like how quickly are you doing it? Are you doing it over the course of 2 seconds? Are you doing it over the course of 0.02 seconds? Like what's going on there? And then the negative is just a negative. The change in phi is measured in Weavers, and the change in time is measured in seconds. I think that's all we need to talk about here for this formula. This formula, sorry, and the reason I bring that up is because this is the formula that is on your formula sheet. Epsilon equals negative n delta phi on delta t. You should be able to find it in the electromagnetism section. So let's jump into a cheeky little practice. The diagram shows an electric circuit in a magnetic field directed into the page. The graph shows how the flux flows through the conductive loop. The flux that flows through the conductive loop changes over a period of 12 seconds. And we want to calculate the maximum induced EMF within the stationary loop during the 12-second interval. Basically, we want to figure out what is the biggest EMF that we can possibly induce here. Now, one of the reasons that I like to think about our formula as a derivative, I'll show you in just a second, sorry. But basically what we need to do is we need to look at our graph and we need to figure out, okay, whereabouts are we going to get a maximum EMF in? And the reason that I like to think of this as a derivative is because a derivative just tells us about the gradient, right? The derivative of a graph just says that what we're looking at here is not the actual thing itself, but what we're looking at is the gradient. Now, in order to get the maximum, that means what we're looking for is we're looking for the point where the gradient is the most shocking, basically where the gradient is the steepest. So in this case, you can kind of spot there's 3 different sections to the graph. We've got this section here where it's kind of sloping upwards. We've got this section over here where it's a bit flat. And then we've got this section where it suddenly drops from a very high value all the way back down to quite a low value in a very short period of time. So just looking at this graph, the sharpest peak, the sharpest gradient, occurs in this last section over here. This is where we've got this really, really sharp drop. So just in terms of looking at this visually, the highest gradient, the biggest gradient is occurring in this section here. So if we're looking for the maximum induced EMF, we're probably looking at this section here. In this case, it is the correct answer. We are actually looking over here, but I just want to pause for a second and I want to say, be careful when you're doing questions like this because of this negative, right? If we are looking for the maximum number, we're looking for the largest positive number. And what you may have noticed over here is that this gradient is actually negative. It's sloping downwards. So if our formula just was like calculating the gradient, this would actually probably give us our lowest possible EMF because it would be a very large but very negative number. And so our maximum EMF would be over here. As it turns out, the formula actually bungs a negative out the front, like we have this negative chilling out here, which means that when we calculate this negative gradient, we then slap a negative out the front, which turns it into a positive number. And so as a result, our net EMF is actually still going to be positive, which is quite lovely, which is exactly what we want. So we can chuck all of that into our, now that we figured, sorry, that was all to say, essentially, in this case, our maximum EMF occurs at this point here because it's the steepest gradient, but also because it's negative. So in general, if we're looking for the maximum possible EMF, we're looking for the steepest negative sloping section. However, it's important to always read the question carefully because sometimes it might just be looking for the maximum magnitude of EMF, in which case it could be like this section over here if it was steeper because the absolute value of that particular EMF would be larger. Okay, that all being said, we finally actually know like what the change is going to be. Sorry, we finally know which region we're actually analyzing, which is this section over here. Now let's actually get to plugging some numbers in. Let's try and calculate this thing. So we've got the negative. We know that this is a single loop. We're told it's one loop, which means that our n is equal to 1, and like the diagram shows that as well. It's just n equals to 1. We then just need to calculate our change in time and our change in flux. Now, looking at the diagram, the period that we're analyzing is this period between 10 and 12 seconds. So hopefully you can think that our delta t is going to be equal to 2 seconds. That's just the way it is. You could calculate that, of course, by doing 12 minus 10, which is equal to 2, but it's still just going to be 2. Trust me. Then our other thing that we need to do is we need to calculate our change in flux. Now, remember, just as a bit of a side note, this is true for physics. This is also true for chemistry, true for, I don't know, it might be true for bio as well. Sorry, no, it's always true, but like, I don't know if you'd use it in bio. But whenever we're calculating a change in something, what we're calculating is we're doing the final of that thing minus the initial. So in this case, we're doing the final flux minus the initial flux. And in our case, our final flux is equal to 0 minus our initial flux, which is equal to 0.6, which if you chuck that on, you can do it in your head. That gives us a change in flux of negative 0.6. So finally, we've got our number of coils as 1. We've got our change in flux is negative 0.6. And we've got, I forgot to write it, but our change in time is equal to 2. So suddenly, we can chuck all of this onto our calculator. We can say our epsilon is, our EMF is equal to negative of 1 times our change in flux, which is minus 0.6, all divided by our change in time, which is 2, which if you chuck all of that onto your calculator, you end up with an EMF of 0.3 volts. And I'm very sorry, I realized I never said it, but this funky looking backwards E thing is what we call epsilon. It's the Greek symbol epsilon. But yeah, so we've got a maximum EMF of 0.3 volts, which is lovely. So that being said, that brings us to what, in my opinion, is probably it's probably the hardest concept of this module and one of the hardest concepts in the entirety of physics, which is my favorite law, my least favorite law, Lenz's law. As Lenz's law says, an induced current must flow such that it creates a magnetic field that opposes the change in flux. Basically, this is where the negative in Faraday's law comes from. It basically tells us that if we have a change in flux, basically if we have a current flowing in one direction, the current that's induced in the other side always needs to oppose it. Whatever changes needs to be acting in opposition. And this essentially comes from the law of conservation of energy. Now, to understand where this comes from, let's do a cheeky thought experiment. So let's imagine what happens when we move a coil of wire through a magnetic field? Now, by Faraday's law, we are going to induce some kind of current. Now, by Lenz's law, the negative, the EMF is going to oppose the motion of the wire, and so basically over time, that current is going to dissipate out to nothing. So essentially, we move the current into the wire, we move the coil into the wire. Sorry, let me express this better. You move the coil into the magnetic field, and by Faraday's law, a current is induced. And by Lenz's law, that current is acting to like oppose the motion of the wire. Basically, if you remember back to the motor effect topic, the current that's flowing through the wire is going to induce a force, and Lenz's law basically just says that the direction of the current is going to be such that the force is acting in opposition to whichever direction you're moving the wire. However, to see sort of why that's important, let's imagine what would happen if the current instead supported the change, basically went in the same direction. Well, if the current supported the change, we would get like even more current because we're moving it even faster through the current. So it would move faster, so we'd get a greater change in flux, so there'd be more current, so we would have suddenly infinite energy, and like, yeah, we've just solved climate change, and oopsie doopsies, we've just made a black hole, and bada bing, bada boom, we've just destroyed the universe. So basically, the law of conservation of energy here is just coming in clutch to save our lives, which honestly I stand, big fan. So Lenz's law is always working to kind of oppose whatever change is happening, and it means that stuff is always going to be not going bazonkers, which big fan. And yeah, um, so let's do a cheeky practice here. Let's try and figure out what what direction is the current going to be induced in the room? Is it going to be clockwise or is it going to be anti-clockwise? So in this situation here, we've got a ring that is being pulled out of a magnetic field. And we need to figure out, well, by Lenz's law says, okay, we need to oppose whatever change is happening. We kind of need to go from this very concrete example, apply that slightly abstract law, and figure out, okay, what is actually going on here? Okay, now the way that I would encourage you to do this is to sort of break it into two steps. So your two steps are going to be, first of all, identify what the change in flux is. So identify, and I told you before, my writing is horrific when I'm trying to write as I'm writing. So identify the change in flux. Figure out like what is that change actually going to be, and then once we've figured out that change in flux, use your right hand grip rule. Right now, a lot of people will say just use your right hand ruler. And while, once again, with the very specific percentages, maybe like 5% of cases, you might need to use your palm rule. All of the other percentage cases, you're going to be using your grip rule. So use the right hand grip rule. Hand grip rule. Yes, because in this case, most of the cases we're going to be using right hand grip rule. To go back to like what I sort of started saying earlier in the lecture, in general, you use your palm rule whenever you're dealing with forces. You use your grip rule whenever you're dealing with currents, or the relationship between currents and magnetic fields. You could also sort of think of that as like you use the grip rule whenever you've got a circle. Whenever there's anything that's in a closed loop, you're probably going to be using the grip rule because like the grip rule moves around in a circle, so it sort of checks out. That's why we use the grip rule there. So in this case, we've got our ring, we're moving it out of a magnetic field, and the first thing we need to do is identify that change in flux. Like what is actually happening? What change in flux is actually going on here? To do that, let's break it down into two situations. Initially, we've got some kind of magnetic field that's going into the page, and then afterwards, we've got no magnetic field that's going into the page. So from the perspective of the coil, we started out with a magnetic field. We then don't have a magnetic field anymore, which means the change in flux is we're losing this magnetic field. Okay? Hopefully that makes sense so far. So we've gone from having no magnetic field to having some magnetic field. Now, here's the step that most people struggle with, which is how do we kind of oppose that change? What can we do to actually like cancel out whatever change was happening? Well, if we lost a magnetic field, the way we can cancel that change is we can reinstate the magnetic field. We can add it back. We can kind of make a fake version of a magnetic field moving into the page. Hopefully that made a little bit of sense. Basically, to recap that, right, we started off with a magnetic field, we lost it, magnetic field disappeared. So to oppose the losing of the magnetic field, like we're trying to oppose the change, which was the magnetic field going kapush. In order to oppose that change, we need to add a magnetic field back in. We basically just need to add these x's back in. And that is our change in flux done. We've identified the change in flux. I should probably add on, we need to figure out like how to oppose that change. But now that we've figured out how to oppose that change, all we need to do is use the right-hand grip rule. And the right-hand grip rule that we're going to be using is on this magnetic flux that we've just drawn down here. So we've got a whole bunch of field lines going into the page. We can just use your right-hand grip rule on those field lines going into the page, right? So just a side note, the right hand grip rule is kind of reversible, so you can it's not strictly like thumb has to be one thing and fingers have to be the other. You can kind of just use it with whatever you've got can be one of them and whatever you've got can be the other one. So in this case, we've got a magnetic field with your thumb pointing into the page. So you can use your fingers to represent the direction of the current that's going to be induced as a result. So you can point your thumb pointing into the page, your fingers can be curling around, and if you do that, you'll see that your fingers curl around in a circle like this, which is pointing in the clockwise direction. And that is how we do this question to apply Lenz's law. So just to recap everything that's going on here really quickly, because I know that a lot of people will really struggle with this. The first thing we did was we identified the change. We said, okay, what was happening? We went from some magnetic field to no magnetic field. Therefore, the change was we were losing our magnetic field strength. That's step one. Step two, we then ask, how do we oppose that change? All right, so we start off by having the change, which was we were losing our magnetic field. Then we needed to oppose it, right? We needed to stop that change from happening. So in order to oppose that change, we sort of reinstate the magnetic field. We add it back. We create our own fake magnetic field instead. So that is what we're trying to do here. And then once we've created that like fake magnetic field, we use our right-hand grip rule to figure out what is the direction of the current that's induced going to be. And so in this case, use your right-hand grip rule and you find out it's going to be pointing in that anti-clockwise direction, which is